So let's move on to Chapter 5, which is on the periodic table. And the first question is, which is the larger atom? And then we move on to which would form a 3 positive ion, and where are the nonmetals, the metals, alkaline earth, halogens, semimetals, etc. Where are the solids, liquids, gases? Why is sulfur smaller than silicon? Why is sulfur bigger than oxygen? Okay, let's pull up a table and start to deal with some of these questions. All right, size-wise, the first thing we would want to say is that francium is the biggest atom of them all, so big fat francium, okay? And that atoms are small up here around helium, okay? So here are the small ones, and here are the big ones, and so we have this general trend for size that goes like this. Okay. The other trends go opposite. So size gets big in the lower left corner. All the other trends, ionization energy, electron affinity, they get big going to the top right. So think about it. A big atom like this can't hold on to its electrons very well, so it's easy to pull them off. And that's why we find that this has a low ionization energy. Ionization energy is the energy it takes to remove an electron. Small atoms, well, the nucleus is close to the surface, and so it's hard to pull away their electrons, and they are able to draw in other electrons, and that's something else called electronegativity. So we find that the atoms over here on the right hand side, which are nonmetals, are good at taking electrons. They are small and they can pull in electrons because their nucleus is close to the surface, but the metals on the left side are large and they have more likelihood to shed electrons and go positive and become cations than to pull an electron. So those trends are ones that you should use to reason through, and if you can keep straight the size of the atoms, that's a great starting point. Which atom would form a 3+ ion? Okay, so in the periodic table we have column numbers which correspond to charges that they would typically carry. So +3 would be this third column. These are all metals. To the left of the stairs are metals, and they become cations, and so a +3 would be something from column 3. Now, going the reverse, we say these noble gases never gain or lose electrons. They're inert. But column 7 is a very reactive column and loves to steal 1 electron, so they are typically adopting a -1 charge on their anions. Column 6 is too shy of perfection. We're saying having 8 outer electrons is perfection, which is what the noble gases have. So oxygen, sulfur, selenium, they tend to exist as a 2- charge, and that gives them the octet. And then we have -3s in column 5. So nitride would be -3. Where are the nonmetals, metals, alkaline earth, halogens, semimetals, noble gases, alkalis, transition metals? Okay, these are all color-coded on your table. In your book, you should know these. These are the alkalis, alkaline earth, the transition metals, the post-transition metals sit under the stairs. The metalloids are on the stairs. They are metal/nonmetals, metalloids. I also want you to know the noble gases and the halogens. It's very important that you understand the big split. This is all metals this way. To the left of the stairs are metals, and that they give away electrons. Over here we have the nonmetals, take electrons. Number 34. Where are liquid, solids, gases on the periodic table? Under normal atmospheric conditions, color coding is shown here. If it's red, it's a gas. Okay, so you can see the noble gases are gases, and also these small atoms over here are gases and hydrogen. And then there are only two elements that naturally occur as liquid. That's mercury and bromine. They're blue, and all the rest are solids. Number 35. Why is sulfur smaller than silicon? Okay, let's get their position here on the table. What we're talking about here. We've got sulfur and we've got silicon. First of all, it is not logical that sulfur would be smaller than silicon because sulfur has more stuff in it. Sulfur has 2 more protons and 2 more electrons and probably some more neutrons. So why would it be smaller? Well, we already said that atoms get smaller over here in this corner, but that's not a good explanation. What we really need to think about is the pull of the nucleus. So it's a stronger positive pull from nucleus. It pulls in the electrons tighter. All of the electrons are in equivalent positions flying around the nucleus, but the fact that we put 2 extra protons into the nucleus pulls the electrons in tighter. So by adding 2 more electrons, we have 2 more pluses to pull in the electrons tighter. Alright, the next comparison is between sulfur and oxygen. And so what we have here is a little more logical conclusion. Here's oxygen. It only has 2 energy shells. Okay, you've got your nucleus, and then you've got the first energy level and the second, and then sulfur's got a third. It's logical that sulfur would be bigger. So going from top to bottom, the growth and the fact that atoms get bigger, that's shell addition. But going from left to right and shrinking, that's nuclear pull. Alright, let's move on to chapter 6 and naming compounds and writing formulas. This is the hardest chapter in the book, and I'm helping you out and giving you the polyatomic ion list on your resource sheet, and that's going to help you a big extent, but you still have to learn the protocols, and the ionic compound naming is the hardest. Covalent, you're going to need to learn your Greek prefixes, and that's memorization. And then the acids, you might as well just memorize that common acid list that I gave you at the beginning of this video series. You need to recognize it as binary or an oxyacid, and they get named accordingly. Alright, so I'm just going to start going through the chapter 6 questions here, and we'll pick up along the way. So lithium oxide, we see this as a metal with a nonmetal, so we know it's ionic. So that's going to say it's one of these 2 things. And ternary means there are 3 kinds of atoms. No, there are only 2 kinds of atoms, so we would call that binary ionic. This is the hypochlorite polyatomic ion. Okay, the fact that it's negative would be a polyatomic anion. You should just learn those so that you immediately recognize the combinations. Alright, what compound would form between iron 3+ and hypochlorite? Well, you have to become familiar with this crisscross method, of which we form a neutral compound. This is an ionic compound, a metal ion with a 3+ charge, and a polyatomic ion with a -1 charge, and they would be in this combination to make a neutral compound. We would call this iron 3 meaning the charge on the metal, hypochlorite. What is the systematic name of HBr? That's hydrobromic acid. We see an H in the front, and we know it's an acid. You should be naming it as an acid, hydrobromic acid. What is the systematic name of S2O6? I see non-metal, non-metal. I go to my Greek method. I say disulfur. No change in the ending of the first element. And then hex oxide. Now, it's a personal preference whether you say hexaoxide or hexoxide. I don't usually put the double vowel in there. Disulfur hexoxide. As long as you learn your Greek prefixes, it's a relief to get these covalent questions. They're pretty easy. What's the systematic name of Na3PO4? I am so programmed to see that as a polyatomic ion, and I call that phosphate. And sodium with phosphate? Well, it's sodium phosphate. That's it. I don't need to say Roman numeral 1 with it because sodium can only have one charge. So we go with the minimal information we need to transmit for someone to write properly. I needed to help out iron because iron is a transition metal, and the transition metals have multiple charge possibilities. But sodium's clear cut, it's +1. If I say sodium phosphate, someone can write that out. What's the charge on the sodium ion in this? I think I've already said. It's +1. It's always +1. Sodium is a column 1 metal. All right, scooting down here to number 44. What's the chemical formula for nitric acid? Nitric acid is based on nitrate. There's nitrate. I put enough hydrogens on it to make it neutral. There's nitric acid, HNO3. Write the chemical formula for barium hydroxide. Here's barium. It's a column 2 metal, so I'm going to be combining that guy with something I wish you would memorize, although I'm helping you with the sheet. That's hydroxide. So I've got to do a crisscross to get that to be a neutral compound. I'll need 2 hydroxides to balance the barium. Write the chemical formula for nickel 2 nitride. Okay, nickel 2 means that's the charge on the nickel. Nitride. It's like the last piece that students get correct. Nitride is not a polyatomic ion. Whoops, I did that wrong. This is nitride, the negative form of nitrogen. When I crisscross this, I get 3 nickels will combine with 2 nitrides. That's your compound right there. Nickel 2 nitride. Looks kind of strange, doesn't it? Alright, totally different kind of question. Compare and contrast ionic, metallic, covalent bonds. Ionic bonds is when the metal is positive and the nonmetal is negative, and they hold together in a plus-minus attraction. Metallic compounds are what we call the electron C. You have multiple metal atoms, and they just hang out next to each other, and the electrons flow around them. There aren't very many electrons, and they're constantly flowing, which is why we say metals are conductive. Lastly, nonmetals form covalent compounds with nonmetals. They share a cloud. They merge a cloud, and it becomes it can be unequal or equal sharing, but the electrons fly around both nuclei. Final Chapter 7. Chapter 7 is on reactions. You need to become familiar with the different kinds of reactions and be familiar with the formats of them so that you can recognize one when presented. So see this reaction? This is calcium carbonate breaking out to calcium oxide and CO2. That's a decomposition reaction. It's where a big thing breaks into small things. We look at aluminums, they check 2, 2. The whole idea is that we have to have the same number of each of atom types on either side of the arrow. Carbons, we've got 3 on the left, 1 on the right, so I fixed the problem. I put a 3 there. Okay? And now we look at our oxygens. I've got 9 oxygens on the left. I need 9 on the right. I've got 6 and 3, that's 9. It checks. We're done. All right, the next one is a solubility question. You should immediately be reaching for the solubility table on your resources sheet. You'll find that all ammonium compounds are soluble, and I'm looking for insoluble. That means it will not dissolve. These always dissolve. Okay, so it's not this one. all potassium compounds always dissolve, and all sodium compounds. We look at strontium hydroxide. We look at the table. We find out that that one is always soluble. And so it's this guy, barium sulfate. How would you name each of the compounds in number 49? Ammonium carbonate, potassium chromate, strontium hydroxide, barium sulfate, sodium sulfide. 52 is an activity series question. Which of the following metals will react with hydrobromic acid? Alright, you need to have an activity series to be able to answer this question, and notice in your class notes I clearly marked, here's hydrogen sitting down here. So hydrogen represents acids because acids give away hydrogen. So any metal that sits above the hydrogen will react with the acid. So on this question, you are asked silver, iron, copper, potassium. Silver sits below, so it will not react. Copper sits below. And then we've got iron sitting above, so iron will react. And potassium definitely will, because potassium's right at the top of the table. So we'd say iron and potassium are our answers on that. Which of the following metals will react with aqueous lead nitrate? Okay, now we're just looking for lead on the table and comparing to these. So, going back to the activity series, checking out their relative positions. Where's lead? Lead's here. So, now we know copper and silver could not possibly bump out lead. They're less active, but the same two, potassium and iron, are more active than lead. So we have the same answer for that question. We have 3 more problems, and these next 2 are the hardest problems on the test. We have so many layers of learning to be able to write compounds successfully. So number 54, write and balance the following chemical reaction equation. So first we have to write the compounds, and then we'll balance the reaction equation to make sure there are the same number of atoms on both sides. Okay, when it says aqueous solution, that means that this is all happening in water, but we don't have to write water in the reaction equation. It's just telling us that there are free ions. So I know that chromium 3 iodide is this. Okay, it means it's chromium 3 plus with I minus, and so it would be this, and I would do an AQ afterwards to say that it's in solution. And sodium hydroxide is this, and it forms a precipitation. So this is one of these double displacement reaction equations where they're trading partners. The chromium gets the hydroxide and the sodium gets the iodide, and we produce chromium 3 hydroxide precipitate. So we could write that as a solid, and actually I should put this as aqueous because those ions, the free sodium and the free hydroxide, are floating around in the water. And sodium iodide is a +1 with a -1, 1-to-1 combination like that. Okay, so we just need to balance this. So since I need 3 hydroxides there, I'll have to get 3 here. I have 3 iodides, so I must have 3 sodium iodides, and you're done. Next question. Sulfuric acid reacts with sodium hydroxide to produce water and aqueous sodium sulfate. Alright, sulfuric acid is H2SO4 based on sulfate, and this would be it's kind of an understood thing, it'd be aqueous. It's not essential that you get the aqueous in there. And sodium hydroxide, we'll say it's aqueous. Most of our reactions that we do in this course are aqueous. Alright, this is the acid-base neutralization. This hydrogen goes with this hydroxide to make water. I can see that I'm going to have an uneven because this is a 2- ion. I'm going to need 2 sodiums to go with it. So I've taken care of the sulfate. I've taken care of, if I put a 2 here, my sodiums are even. And then I have 2 OHs here. They're actually OH minuses. Okay, I have 2 OH minuses. And from the sulfuric acid, I have 2 H pluses. And you'll get used to the idea that this makes 2 waters. That's the acid-base neutralization producing water. We're done. Okay? This is officially a liquid. It's not ions in solution. It's not aqueous. So that's liquid, and this would be aqueous. Which of these elements is not written in its natural state? You need to have a periodic table. You also need to know your diatomic gases. What are those diatomic gases? These are the diatomics. These are the gases that naturally occur as 2 atom combinations. And then the whole halogen series. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. They're the diatomics. So that's normal for hydrogen to be like that. Copper is normally a solid. Fluorine's on this list of diatomics. Zinc is normally a solid. Mercury is normally a liquid. Bromine's normally a liquid. Argon is a gas. And silver is not a liquid. And that's it. We went through the whole midterm. Good luck. Let me know if you have any questions.